Thank you so much, Joyce. Good morning, everyone. It's great to be back here at Q2B. So today I will be speaking about the work that we are doing at Entropica Labs. And if you're not familiar with the company, we're based in Singapore. We are a software quantum computing company. And what we're building is a software stack to manage and enable fault-tolerant quantum computing. The fundamental motivation for a talk, and in fact, if you've been following the news lately, if you were in the room this morning, is that quantum systems are inherently noisy. And we need to be able to fire off the noise to make them useful. And in fact, it's most likely that we are going to need fault-tolerant quantum computers if we want to unlock the financial value of the devices. As you have noticed, there's been a lot of interest in quantum error correction lately. And what is really fantastic is that the industry overall is focusing more and more to advance towards fault tolerance. And in fact, if you have been looking at the roadmaps and the timelines that pretty much all of the hardware companies have presented lately, what you will see is that they have set 2029 as a date where they expect to have fault-tolerant quantum computers available. It may not mean that they're going to be millions of qubits, fully fault-tolerant, and capable of supporting any quantum computation. But what I think is very important to emphasize here is that the industry is eyeing fault tolerance and is approaching way faster maybe than many ever had anticipated before. So what do we need for that to happen? Well, we need at least three things. We need better hardware, better control, to make sure that the qubits behave as they should. And I think nobody would have any doubt about that. Everybody would agree with that statement. But there is another component which is actually very important. And I'm pretty happy that David from Quantinuum earlier has also emphasized this point. We need quantum error correction software. We need software to manage the fault-tolerant part of the stack. And this is actually a much more difficult task than maybe people give credit for. And this is also what I want to talk about today. So the quantum ecosystem has multiple needs. And it really depends whether you're a researcher, whether you're a hardware company or working for a hardware company or control company, or whether you work in industry, or if you're a developer who wants to use a quantum computer. Now, some of the needs overlap. It's kind of nice to look at them separately. So if you're a researcher, your goal is to increase research results. Kind of goes without saying. What you're going to need when it comes to software are tools so that you can design, validate, and implement new quantum error correction schemes, new quantum error correction code structures. Today, a lot of this work is still mostly manual. There are very few tools that allow you to do that, although it's nice to see that tools like Steam and Crumble, if you're familiar with them, have become widely adopted in the industry. If you work for a hardware company, then what you want to do is to accelerate the path to fault tolerance. And there's a lot of work that needs to happen for that. So you want to be able to embed code into the fault-tolerant physical operations. When I say code here, I mean error correction code. But you also need to think about how you're going to orchestrate the data flow and manage the detect, decode, correct pipeline. Quantum error correction is such a fundamental part of a quantum computing that in a way you can think of all the software infrastructure that you require to run fault-tolerant error correction properly as some sort of operating system for a quantum computer. And at the end, if you're a user of a quantum computer, what you want to do, you want to operate and work at a very high level. You want to be able to code in a high-level programming language, write a quantum program, and run it on a quantum computer without having to worry about how error correction and fault tolerance are managed. In a way, all of that needs to happen on the back end for you. With these needs in mind, then I'll introduce the Loom, which is the core of the quantum software stack, and is what we are building at Entropica. It is a software platform, it's entirely software, to automate quantum error correction workflows. This is how it works. If you're a user of a quantum computer, it takes as input an application, an algorithm, a quantum program, and it transforms it into a fault-tolerant implementation, which is a sequence of physical operations that can run on a quantum computer that are provably fault-tolerant, and then allows you to run on multiple quantum computers. And the goal, the key really is to unlock fault tolerance. And the value proposition of Loom spans, again, the needs that I just introduced previously. First of all, it allows you to generate fault-tolerant circuits easily, which is really the key, especially thinking ahead at the moment when we are going to have multiple fault-tolerant quantum computers available. And it removes all the complexity of quantum error correction so that you can fully focus on the application and the algorithms. But there is another aspect which I think is incredibly interesting, especially if you work for a hardware company. There's going to be a transition period which is starting pretty much today, or in these days, or in 2024, all the way to, let's say, 2029, 2030, where we are going to have maybe hundreds, thousands, few thousands of physical qubits, and let's say all the way up to 100 logical qubits. And in that regime, every qubit matters. The resources available to you are incredibly important. You want to optimize the resources that you have so that you can squeeze as much value from, let's call them, early fault-tolerant quantum computers. And the last point is that when you have software tools available, you can supercharge your quantum error correction team. I'm pretty sure everybody here is familiar with the difficulty of hiring experts in quantum error correction because there are simply not many. It used to be a pretty niche part of quantum information overall. And today, we lack the expertise that we need to really accelerate error correction when it comes to human resources. So we want to be able to supercharge the people that we have. We want to give them the tools so that they can do their work better, faster, and more efficiently. And this is really where the Loom comes into the picture. So the software stack that we are building at Entropica is actually more colorful, more complex than just that. There are different elements within the Loom, which I'm going to introduce today. So the first one is the workbench. The workbench is a graphical user interface the users can access to design and optimize quantum error correction codes. And later into the presentation, I'm going to show you a video of how the workbench looks like. I will spend a little bit of time on the ECA because this is something I'm actually very proud. So the team has put a lot of work in defining and constructing a context-rich data structure that you can use to represent and implement quantum error correction codes. I think it's very interesting that, at least to the best of my knowledge today, there are no data structures available to you if you want to work specifically with quantum error correction. Well, the ECA solves the problem. If you want an analogy, you can think of it as a JSON format for error correction. It includes all the information that you need to run your error correction code, and it makes it very easy to transfer this information between the user or between different elements of the stack and the quantum control of your quantum computer. The last element is a EDB, which is a database tool that allows you to store the results of your quantum computation, share them efficiently with your team, and let the team work with the data and, for example, run machine learning or data analysis applications on that. This is just to give you an overview of everything that we're building at Entropica, but it's also important for you to visualize how the stack looks like and what is the user experience if you want to access our software tools. So the workbench is really the user interface so that you can design error correction codes. And it's all powered by the Loom, which works at the back end. So you have a visual front end and a quantum error correction SDK, a software development kit. With that, you generate quantum error correction program, which are defined as loom.eca. And you can serialize them into ECA structures. So these are, as I said just now, these are quantum error correction data structure that will then get interpreted by basically by the software stack that sits within the control hardware of a quantum computer. So everything that happens inside the dotted box happens within the Entropica framework, and then it gets passed to the hardware, and eventually to the quantum computer. And this is very neat. This is a very neat way to work, and it allows you as a user to operate across multiple devices and also to choose your entry points. To make it all more real and more concrete, I want to give you an example of what we are already able to do with Loom. This is a simple example, but it's a very meaningful one. It's called the quantum alpha adder, which is basically 1 + 1. So it's always great to start from first principles. So what if you want to implement 1 + 1 on a quantum computer using the surface code? Then what you would do, you would pass the logical circuit, which is what you see here on the left hand of the slide. You would pass it to Loom, and what Loom returns to you is the implementation given the surface code with a certain distance, in this case, distance 3, telling you what the patches are and what the lattice surgery operations are to implement this logical circuit. It gives you the full decomposition in a fault-tolerant way. I'm not showing you the circuit because it's maybe not ideal to show on a slide, but you can easily get the whole circuit. Here is just a pictorial representation of what the translation looks like given the surface code. But it doesn't only give you that. You can also immediately extract the resources that you need to implement the quantum alpha adder with the surface code distance 3. So the number of gates, the depth of the circuit, and the number of physical qubits that you need. You can think of it as the canonical representation for the surface code of the quantum alpha adder. If you were to do everything by hand, if you want to derive it yourself, or if you want to write program to do it, well, it's a painful work to do. And the Loom automizes all of that process. But there is another example which I think is even more interesting, and it is in a way a byproduct of using the tools that we've built. So imagine you want to start with a different logical circuit. You want to prepare a GHZ state. Simple one, 3 qubits. Well, Loom immediately gives you a canonical representation to do that with the surface code, where you would have 4 patches, 3 for the logical qubits and 1 for the ancilla qubit that you need. Okay, so far nothing unusual, right? But actually the team came up with different potential implementations, potential fault-tolerant implementations of the GHZ state preparation circuit. And he said, well, sure, we can work with the canonical one, but we can also work with different ones. We can expand the ancillary patch, for example, or we can start with a larger logical patch and split it into 3. 3 because each one of them represents one of the logical qubits of the circuit. So which one is better? Like today, if I ask any of you which one is better, you would have to go do the calculations and then come back later, maybe after a couple of days, and tell me. But actually, with our tools, we could do 2 things. The first one is to show that even if it looks appealing and potentially more efficient than the canonical representation, the middle one is actually incorrect. It is not a faithful representation of the logical circuit. And we could show that by using the validation tools that are built within Loom. They tell you whether the representation from logical to physical is correct, and it represents the circuit that you want to implement. Okay, so one is out of the picture. But then what gets even more interesting is that you can look at the precise resources that you need, and what you find is that the splitting one, the one that was proposed after by the team, is way more efficient when it comes to number of gates, to depth of the circuit, and number of physical qubits that you require. So the canonical one would take, for example, for distance 3 surface code, about 100 qubits, but with the splitting one, you only need 65. It is really important if you have a small-scale quantum computer and you want to maximize the usage of your qubits. Now, you can save about 1/3 of the qubits, and the depth of the circuit is reduced by, well, almost to 20% of the canonical one. This becomes even more relevant if you have distance 5, right? So the message here is that when you have powerful tools available to you, you can come up with really interesting logical implementations of quantum circuits, which saves you a lot of resources. And it goes back to this idea of supercharging your quantum error correction team, right? And using in the most efficient way the quantum computers that are going to be available to us between now and having a fully fledged fault-tolerant quantum computer. So I'm going to conclude one thing that I want to share with you is a roadmap for 2025. In fact, the Q1 roadmap for 2025. Everything I'm speaking about is already functioning and is going to be available if you're interested, well, pretty much tomorrow, starting January. We're going to launch in beta the Workbench. We're going to open up an early access program for the Loom. And well, I think this is also very interesting, is that we're going to launch what we call the machine learning fault tolerance pipeline, which is based on reinforcement learning. And it is a tool within the Loom that allows you to discover and optimize new fault-tolerant error correction circuits, which is very similar to what I just showed you for the GHZ state, but instead of having to come up with the circuits yourself, we're going to leverage machine learning for that. And I promise that I will show you how the Workbench looks like, and this is a Workbench in action today. If any of you were in Tokyo just a couple of months ago for Q2B Tokyo, you would have seen a more primitive version of the Workbench. The team has done a lot of work to really polish it. And the way it works, it allows the user to drag and drop and very quickly design topological quantum error correction codes, which then you can export as ECA files and go and implement them on any quantum computer that you would like. But most importantly, what I'm very pleased to announce today is that we're partnering with some of the leading companies to do all of this work. In fact, software, Horizon Quantum, control hardware, quantum machines, and hardware and software, Xanadu. So with Horizon, we are working on automatically deploy quantum error correction workflows in a way that is very developer-friendly. With quantum machines, what we are doing is to make sure that we can express quantum error correction schemes that are designed with our tools in QA. And we're going to test all of that on the IQCC. And with Xanadu, what we are planning to do, what we just started, is software integration so that we can utilize the qubits available to us in the most efficient way, working towards fault-tolerant quantum computing. And if you're interested in the collaboration with Horizon, well, that's great, because on Thursday at 2:20 p.m., I'm going to be speaking about that together with Joe. And I'm going to show you what you can do with Loom and Triple Alpha. So let me conclude. Useful applications of quantum computing will require fault tolerance. And the message of the talk is that to enable all of it, we don't only need hardware. We need software specialized for error correction and fault-tolerant error correction to manage all of that incredibly complex part of the stack. So if you're interested in anything that I've shown to you, I'll be around for a full conference, so please come and talk to me. Otherwise, you can reach out to us if you want to join the Loom Early Access Program. And again, thank you so much.